thing. You need new injectors. It's going to cost you at least $800, maybe more. But this old mechanic, who had been working on engines since before fuel injection was even standard, just smiled and said something I will never forget. In Japan, we don't replace what we can restore, and a dirty injector is not a broken injector. It's just an injector that forgot how to spray properly. He explained that in Japanese automotive culture, the idea of replacing a component that simply needs cleaning is almost offensive. It's wasteful, it's expensive, and most importantly, it's unnecessary. The real secret isn't some magical product or expensive equipment. It's understanding how fuel injectors actually get dirty, why they lose their precision, and how to reverse that process using methods that work with the engine's design, not against it. What you're about to learn is exactly that. 10 proven methods used by the most disciplined mechanics in Japan. Methods that clean from the inside, that restore spray patterns, that bring back throttle response, and that cost a fraction of what a replacement would. And the best part, not a single injector needs to come out of the engine. Before we dive deep into these techniques, I need to know something. Where are you watching this from? Drop your city in the comments, hit that like button so this reaches more people who are tired of being told they need to replace perfectly good parts, and subscribe, because what's coming next will save you serious money. Alright, let's get into it. Here begins the true Japanese method for cleaning fuel injectors without removal. Number 10. Diagnostic pulse testing without disassembly. Most mechanics will tell you that you can't really know if an injector is clogged without removing it and putting it on a flow bench. But the Japanese have developed a diagnostic method that's so precise, it can tell you exactly which injector is struggling and by how much, all while it's still bolted to the engine. This is done using a professional scan tool that can command individual injectors to pulse at specific intervals while monitoring real-time data from the oxygen sensors, fuel trims, and even the slight variations in crankshaft speed during each cylinder's power stroke. The philosophy here is simple. Before you clean anything, know exactly what you're dealing with. A mechanic in Osaka once told me, "You don't clean a house without first knowing which rooms are dirty." Same with injectors. If cylinder 3 is the problem, why waste time and chemicals treating all 6? The beauty of this diagnostic approach is in its precision. Modern fuel injection systems operate with tolerances measured in milliseconds and microliters. An injector that's even 10% restricted can cause noticeable drivability issues, but that same 10% restriction is almost impossible to detect with traditional diagnostic methods. You might see a slightly rich or lean fuel trim, but that could be caused by a dozen different things: a vacuum leak, a faulty mass airflow sensor, a weak fuel pump. Even a dirty air filter can throw off the readings enough to mask an injector problem. But when you command each injector individually and watch what happens to the engine's response in real time, there's nowhere for a failing injector to hide. The test itself is methodical. The engine is brought to full operating temperature first because cold injectors behave differently than hot ones. A partially clogged injector might work perfectly fine when the fuel is cold and thin, but as soon as the engine heats up and the fuel volatility changes, the restriction becomes apparent. Once at temperature, the scan tool sends a pulse command to injector number 1 while keeping all others closed. The oxygen sensor downstream from that cylinder will immediately show whether the air-fuel mixture is correct, too rich, or too lean. At the same time, the crankshaft position sensor data reveals whether that cylinder is producing power smoothly or if there's a hesitation in the rotation. This data is recorded. Then the same test is performed on injector number 2, then 3, then 4, and so on until every single injector has been evaluated independently. The procedure starts with the engine at full operating temperature. The scan tool sends a command to fire each injector individually while the others remain closed. During this test, the oxygen sensor data will show if that particular injector is delivering too little fuel, indicated by a lean condition, or if it's dribbling when it should be closed, indicated by a rich condition. The crankshaft position sensor, which most people think only tracks ignition timing, actually reveals microscopic hesitations when a cylinder isn't producing the power it should. A healthy injector will cause a smooth, predictable change in engine speed. A clogged one will cause a stumble, a delay, or an uneven power delivery that the sensor picks up instantly. What makes this method so valuable is that it gives you a baseline. You know, before cleaning, whether you're dealing with a partially restricted injector that just needs a good chemical flush, or a mechanically damaged injector that's beyond saving. In Japan, they document these numbers, clean the system using one of the methods we're about to cover, and then retest to confirm the improvement. It's not guesswork. It's measurable, repeatable, and scientifically sound. And here's the interesting part. In many cases, an injector that seems completely dead is actually just so clogged that it can't respond to the standard pulse width. Once cleaned, it comes back to life as if nothing was ever wrong. Number 9. Deep cleaning additives in controlled cycles. If there's one product that gets both praised and criticized in equal measure, it's fuel injector cleaner. The Japanese approach to additives, however, is completely different from what most people do. They don't just pour a bottle into a full tank and hope for the best. They use a very specific protocol that maximizes the chemical's contact time with the deposits while minimizing the risk of dislodging large chunks that could clog downstream filters or damage the structure needed to dissolve hardened varnish and carbon. The reason PEA works where other chemicals fail comes down to molecular polarity. Fuel injector deposits are primarily composed of long-chain hydrocarbons that have been partially oxidized and polymerized by heat. These deposits are hydrophobic, meaning they repel water, but they're also resistant to simple petroleum solvents because they've already been exposed to gasoline for thousands of hours without dissolving. PEA is different. It's an amphiphilic molecule, meaning one end is attracted to hydrocarbons while the other end is attracted to polar substances. This allows it to penetrate the deposit from both sides, breaking the molecular bonds that hold the carbon matrix together. But here's where most people go wrong. They add the PEA-based cleaner to a full 60-liter tank, which dilutes it down to a concentration so low that it might take 500 kilometers of driving before any meaningful cleaning occurs. By that time, half of the chemical has already been burned in the combustion chamber without ever touching the injector tips. The Japanese method maximizes concentration by adding the entire bottle to the smallest amount of fuel possible. This creates a shock treatment that hits the injectors with 10 to 15 times the normal concentration of cleaning agent. Add the entire bottle to a nearly empty tank, no more than 2 or 3 liters of fuel remaining. This creates an extremely high concentration of cleaner to gasoline, much higher than the bottle's instructions suggest. Then, fill the tank only halfway. Drive the car gently, no hard accelerations, no high RPMs, for exactly 30 to 40 kilometers. The goal here is to allow the concentrated solution to soak into the injector nozzles, softening the deposits without subjecting them to high pressure that could break off large pieces. After this gentle cycle, fill the tank completely with premium fuel and drive normally. The deposits, now softened and partially dissolved, will exit the injectors as fine particles that burn completely in the combustion chamber. The timing of this procedure matters as much as the concentration. If you do this cleaning and then immediately drive aggressively, you risk breaking off large chunks of carbon that can clog the fuel filter or damage the catalytic converter when they burn incompletely. The gentle driving period is not optional. It's a critical part of the process. During this time, the PEA molecules are working their way into microscopic cracks and crevices in the deposit layer, weakening the adhesion to the metal surface without causing mechanical fracture. Think of it like soaking a dried-out sponge. If you try to bend it while it's dry, it cracks and breaks. But if you let it absorb water first, it becomes flexible and can be shaped without damage. Same principle applies here. The Japanese repeat this process every 5,000 to 8,000 kilometers, not as a repair, but as prevention. They understand that fuel quality varies, that ethanol blends attract moisture, and that even the best gasoline leaves microscopic residues over time. A master mechanic in Nagoya once explained it perfectly. An injector that's cleaned regularly never gets dirty enough to fail, but an injector that's ignored for 100,000 kilometers becomes a restoration project, not a cleaning job. The difference between the two is about $700 and a lot of frustration. Number 8. Precision precision spray pattern restoration with pressure-regulated cleaning. This is where things start to get serious. While additives work slowly over time, pressure-regulated cleaning delivers immediate and dramatic results by feeding the injectors with pure cleaning solvent under controlled pressure, bypassing the fuel tank entirely. The equipment used in Japanese shops for this procedure is not something you'll find at a typical quick lube place. It's a specialized machine that connects directly to the fuel rail after disconnecting the vehicle's fuel pump. The engine is then started and runs exclusively on a powerful detergent solution that's fed at precisely the same pressure the fuel system normally operates at. The pressure at too low a pressure, it won't atomize properly, and the injectors will dribble rather than spray. The chemicals will pool in the intake ports or combustion chamber instead of being distributed evenly, and the cleaning effect will be minimal. But if you feed the solvent at too high a pressure, you risk damaging the injector's internal spring mechanism, distorting the pintle valve, or even rupturing the seals that keep fuel from leaking externally. Japanese cleaning machines use electronic pressure regulators that monitor the fuel system's pressure sensor in real time and adjust the cleaning solution's pressure to match exactly what the engine control unit expects to see. This means the injectors operate in their normal range of motion, the spray pattern remains consistent, and the cleaning solvent passes through every internal passage, every filter screen, every tiny orifice that fuel normally travels through. It's not just spraying cleaner at the injectors, it's simulating perfect operating conditions while using a chemical that's exponentially more powerful than gasoline. What makes this method so effective is the concentration. Instead of a 1% additive mixed with 50 liters of gasoline, the injectors are now receiving 100% cleaning solution. Every pulse, every spray, every opening and closing cycle is moving pure chemistry through those tiny nozzles. The carbon deposits, the varnish, the gummed-up residues that have been building for years, they all start to soften and break apart within minutes. The procedure typically lasts 15 to 20 minutes, during which the engine might sound slightly different, the exhaust might emit darker smoke, and there might be a chemical smell in the air. All of this is completely normal. It's the visual and olfactory evidence that decades of accumulated junk is being incinerated and expelled. During the cleaning cycle, the technician will vary the engine speed from idle up to about 2,500 RPM and back down again, creating different flow conditions through the injectors. At idle, the injector pulse width is very short, sometimes only 2 to 3 milliseconds. This creates a fast, sharp cleaning action that focuses on the nozzle tip where deposits accumulate most heavily. At higher RPMs, the pulse width increases to 8 or 10 milliseconds, which allows the cleaning solution to flow deeper into the injector body, cleaning the filter screens and internal passages that are upstream of the pintle valve. By cycling through these different operating conditions, the entire injector gets thoroughly cleaned from top to bottom. Japanese technicians monitor the engine's behavior throughout the process. If the idle smooths out, if the throttle response sharpens, if the misfires disappear, they know the cleaning is working. If there's no change, they know the problem might be mechanical, not chemical, and further diagnosis is needed. But in about 85% of cases, this method alone is enough to restore injectors to near original performance. The cost is usually between $120 and $180, which compared to $800 for new injectors makes this an absolute no-brainer. And the best part? It can be repeated as many times as needed without harming the injectors, the seals, or the fuel system. Now, here's a question for you. Have you ever tried one of those cheap fuel additives and felt like it did absolutely nothing? You're not alone. Drop a comment and let me know your experience, because what's coming next will explain exactly why most of those products fail. Number 7. Certified top-tier gasoline as a cleaning agent. This might sound too simple to be a real method, but in Japan, the type of fuel you use is considered the first line of defense against injector contamination. And I'm not talking about octane rating. I'm talking about the detergent package that comes blended into the gasoline at the refinery. In many countries, fuel standards only require a bare minimum of detergents, just enough to prevent gross deposits but not nearly enough to actually clean existing buildup. Top-tier gasoline, which is a certification developed by major automakers, contains 3 to 5 times more detergent additives than the minimum required by law. The difference is enormous. Regular gasoline might keep injectors from getting worse, but it won't make them better. Top-tier gasoline, on the other hand, has been proven in laboratory tests to reduce deposits by up to 45% over the course of just 5,000 kilometers. The detergents work by forming a protective layer on metal surfaces, preventing carbon from adhering in the first place and slowly lifting off deposits that are already there. It's a passive cleaning process that happens every single time you drive. No special procedures, no additional costs beyond the slightly higher price per liter, and no risk of damaging anything. A Japanese fuel chemist I spoke with explained remains stable up to 400 degrees, which means they're still working even when the injector tip is glowing red hot during high load conditions. This is crucial because most deposit formation happens precisely at these high temperatures when fuel residue gets baked onto metal surfaces. The Japanese method here is incredibly straightforward. Use top-tier certified fuel exclusively, not occasionally, not when you feel like it. Every single fill up for the entire life of the vehicle. The cumulative effect is staggering. Engines that run on top-tier fuel for 200,000 kilometers show injector tips that look almost new under magnification. Engines that run on bargain fuel for the same distance show tips that are encrusted, deformed, and barely functional. It's not a miracle. It's just chemistry applied consistently over time. And if your country doesn't have widespread top-tier availability, the Japanese recommendation is to use the fuel from major branded stations and supplement with a high-quality additive every 10,000 kilometers. It's more expensive than doing nothing, but far cheaper than injector replacement. Number 6. Thermal cleaning through high-temperature driving cycles. Here's something most people don't realize. Fuel injectors are self-cleaning to a certain extent, but only if you give them the conditions they need to do it. And those conditions are heat, velocity, and complete combustion. The problem is that most modern driving doesn't provide any of those things. Short trips, city traffic, cold starts, these are all injector killers because they allow deposits to form without ever reaching the temperatures needed to burn them off. The Japanese have a specific term for this, cold sludge accumulation, and they combat it with a technique that's as old as internal combustion itself: sustained, high-temperature operation. Understanding why this works requires a brief look at combustion chemistry. When an engine runs cold, fuel doesn't vaporize completely before ignition. Some of it remains in liquid form, clinging to the cylinder walls, the piston top, and yes, the injector nozzles themselves. This liquid fuel undergoes partial oxidation, creating aldehydes, ketones, and other organic compounds that are sticky and highly reactive. Over time, these compounds polymerize, forming long molecular chains that harden into the brown or black varnish you see on dirty engine components. At low temperatures, say below 400 degrees Celsius, this process is irreversible. The varnish is stable and continues to build up layer after layer. But at temperatures above 600 degrees, something remarkable happens. The thermal energy is high enough to break the covalent bonds holding those polymer chains together. The molecules essentially crack apart and revert to simpler hydrocarbons that can be burned as fuel. This is called pyrolysis, and it's the same principle used in industrial cleaning ovens that burn off organic residues. The difference is that in an engine, you don't need a separate oven. The combustion chamber itself becomes the oven when you run the engine under sustained load at high RPM. The procedure is deliberate. Once a month, take the car on a highway drive of at least 30 continuous minutes at speeds between 90 and 110 kilometers per hour. The engine should be in its optimal operating range, not lugging in too high a gear, not screaming in too low a gear, but running smoothly between 2,500 and 3,500 RPM, depending on the vehicle. During this time, the combustion chamber temperatures rise to around 650 to 750 degrees Celsius. The exhaust manifold manifold glows dull red if you could see it, and the injector tips reach temperatures where soft carbon deposits literally sublimate into gas and exit through the exhaust. The timing here is crucial. It takes about 10 minutes of sustained high-load operation for the entire combustion chamber to heat soak to the point where thermal cleaning begins. If you only drive hard for 5 minutes and then slow down, the temperature drops before any significant cleaning occurs. But if you maintain that load for 30 minutes or more, the cumulative effect is substantial. Not only do the injector tips get cleaned, but so do the intake valves, the piston crowns, the spark plug electrodes, and even the early stages of the exhaust system. It's a whole engine detox that happens naturally as a byproduct of proper operation. What's happening at the molecular level is fascinating. The varnish and gum that build up during low-temperature operation are held together by weak hydrogen bonds. These bonds are stable at 150 degrees but completely unstable at 600 degrees. When you run the engine hot, they don't wait for symptoms. They don't wait for codes. They just drive the car hard enough and long enough to keep everything clean. There's something else worth mentioning about this method. Modern engines with advanced emission controls, particularly those with particulate filters or three-way catalytic converters, are actually designed to undergo periodic regeneration cycles where the exhaust temperature is deliberately raised to burn off accumulated soot. If you never drive your car hard enough to trigger these cycles, the emission system gradually clogs up, which not only reduces performance but can lead to very expensive repairs. By performing regular high-temperature driving, you're not just cleaning the injectors, you're also maintaining the emission system exactly as the engineers intended. There's a secondary benefit that often goes unnoticed. High-temperature cycles also clean the oxygen sensors, the catalytic converter, the EGR valve, and the intake valves. All of these components suffer from the same low-temperature sludge problem, and all of them benefit from the same solution. An Italian mechanic I know jokes that the best diagnostic tool is the Autobahn. He's not entirely wrong. Many minor performance issues resolve themselves after one good high-speed run, simply because the engine finally got hot enough to clean itself. Of course, this method has limits. It won't remove heavy deposits or mechanically damaged spray patterns, but as a preventive measure, it's free, it's effective, and it's something every car should experience regularly. Quick pause here. If you've been following along and you're thinking, this actually makes sense, do me a favor. Share this video with someone who's been told they need new injectors. You might save them hundreds of dollars, and if you haven't subscribed yet, now's the time. We're about to get into the truly advanced techniques. Number 5. Direct rail injection cleaning without fuel pump disconnect. This method bridges the gap between additive treatments and full professional service. It involves injecting a concentrated cleaning solution directly into the fuel rail while the engine is running, allowing the cleaner to pass through the injectors at normal operating pressure and temperature. What makes this different from tank additives is the concentration and the control. The solution doesn't have to travel through 60 liters of gasoline, a fuel filter, and a long fuel line before it reaches the injectors. It goes straight to the source. The equipment is relatively simple: a pressurized canister filled with high-grade injector cleaner, a hose with a quick connect fitting that attaches to the fuel rail's test port, and a regulator to match the system's fuel pressure. The vehicle's fuel pump remains active, but the feed line from the tank is clamped or temporarily disabled, so the engine draws only from the cleaning canister. The engine is started and allowed to run at varying RPMs from idle to about 3,000. cycling through different loads to ensure every injector gets thoroughly flushed. Japanese technicians use this method when they suspect moderate contamination but don't want to commit to a full service yet. It's diagnostic and corrective at the same time. If the engine smooths out during the cleaning, they know the injectors were the problem. If there's no change, they look elsewhere. The process typically uses about half a liter of cleaner and takes around 20 minutes. The exhaust will smell strong, almost like acetone or paint thinner, because that's essentially what's burning in the cylinders. It's not pleasant, but it's temporary, and the results speak for themselves. One important consideration that the Japanese always emphasize is post-treatment procedure. After running on pure cleaner, the fuel system needs to be purged of residual chemicals before returning to normal operation. This is done by reconnecting the fuel line, running the engine on regular gasoline for a few minutes, and then performing a fuel system pressure test to ensure there are no leaks from the fittings that were temporarily disconnected. Skipping this step can lead to rough rough running or even damage to rubber components that aren't meant to sit in concentrated solvents for extended periods. Done correctly, this method can restore up to 70% of the lost injector performance in a single session. Number 4. Ultrasonic cleaning adaptation for installed injectors. Ultrasonic cleaning is well known in the industry as the gold standard for removed injectors. The injector is submerged in a tank of cleaning fluid, and high-frequency sound waves create microscopic bubbles that implode against the metal surface, dislodging even the most stubborn deposits. But removing injectors is labor-intensive, requires special tools, and risks damaging O-rings or electrical connectors. So the Japanese developed a way to bring ultrasonic cleaning to the injector without taking it out of the engine. The device is a portable ultrasonic probe that attaches directly to the exterior of the fuel rail. The physics behind ultrasonic cleaning is both elegant and brutally effective. The probe generates sound waves at frequencies between 20,000 and 40,000 Hz, far above what human ears can detect. These waves travel through the metal of the fuel rail and into the fuel itself, creating alternating zones of high and low pressure. In the low-pressure zones, microscopic bubbles form in the liquid. This is called cavitation. Then, as the pressure wave reverses, those bubbles collapse violently, creating localized shock waves and temperatures that can briefly exceed 5,000 degrees Celsius in a space smaller than a grain of sand. When these cavitation events occur near a surface, such as the inside of an injector nozzle, they create a scrubbing action that's far more effective than any chemical alone could achieve. The shock waves physically dislodge particles that are mechanically bonded to the metal, breaking the adhesion without scratching or damaging the underlying surface. It's like having millions of tiny hammers working simultaneously on every square millimeter of the injector's internal passages. Carbon deposits, varnish, gum, even metal oxides that form from corrosion, all of it can be broken loose by sustained ultrasonic energy. The science behind it is elegant. Ultrasonic vibrations travel through metal far more efficiently than through air. When the probe is activated against the fuel rail, those vibrations propagate through the aluminum or steel sonic tank. The deposits fracture, separate from the metal, and are flushed out during normal injector operation. The entire process takes about 15 minutes per rail, and the engine doesn't even need to be running. But there's a critical parameter that must be controlled, and that's the frequency of the ultrasonic waves. Too low, and the bubbles that form are too large. They collapse with less violence and don't penetrate into narrow passages. Too high, and the bubbles are too small. They don't carry enough energy to dislodge hardened deposits. Japanese ultrasonic cleaning systems use variable frequency generators that can sweep through a range of frequencies, typically 25 to 35 kHz, to ensure maximum effectiveness across different types of contamination. Soft, recent deposits respond best to lower frequencies. Hard, baked on carbon requires higher frequencies. By sweeping through the range, the system addresses both. The procedure also involves careful monitoring of the cleaning solution's temperature. Ultrasonic cavitation is most effective when the liquid is between 50 and 60 degrees Celsius. Below this temperature, the viscosity is too high and bubble formation is inhibited. Above this temperature, the vapor pressure of the liquid increases, and the bubbles don't collapse as violently because they're partially filled with vapor rather than being true cavitation voids. Japanese technicians use thermocouple probes to monitor the fuel rail temperature during the cleaning process, adjusting the ultrasonic power output to maintain optimal conditions throughout the entire session. What I find remarkable about this method is how non-invasive it is. There's no disassembly, no risk of introducing contaminants, no chance of cross-threading a fuel line or damaging a sensor connector. You're literally cleaning the injectors through the walls of the fuel rail using sound waves. It sounds like science fiction, but the physics are solid, and the results are measurable. Japanese shops that use this technique report success rates above 80% for injectors with moderate to heavy carbon buildup. The remaining 20% are usually cases where the deposits are so severe that they've physically deformed the nozzle, or where there's an electrical fault unrelated to contamination. The cost is higher than a simple additive treatment, but lower than traditional removal and bench cleaning. Most Most shops charge between 150 and 250 euros depending on the engine configuration. For a V6 or V8, where removing injectors means dismantling half the intake manifold, this method is an absolute game changer. It's also repeatable. Unlike mechanical cleaning methods that can wear down components over time, ultrasonic energy doesn't cause any physical abrasion. You could theoretically do this every 50,000 kilometers for the entire life of the engine without any negative effects. Alright, we've covered 5 methods so far, and if you've been paying attention, you've probably noticed a pattern. The Japanese don't rely on one miracle cure. They use a combination of techniques tailored to the specific condition of the engine. If you're thinking about which method would work best for your car, drop a comment with your symptoms, mileage, and fuel type. I read every single one, and I'll point you in the right direction. Number 3. Professional flow bench testing and chemical restoration. And this is the method that separates hobbyists from professionals. A flow bench is a piece of equipment that measures exactly how much fuel an injector delivers over a specific time period at a specific pressure. It's the only way to objectively determine whether an injector is performing within manufacturer specifications or if it's falling short. In Japan, many specialized shops offer a service where they test the flow of each injector while it's still installed, then use targeted chemical treatments to restore the ones that are underperforming, and only remove the ones that are mechanically failed. The testing procedure uses a return line adapter that allows fuel to be routed through a calibrated measuring cylinder instead of into the combustion chamber. The engine isn't running, but the fuel pump is activated, and the injectors are pulsed open using a signal generator. A healthy injector will deliver a consistent atomized spray that measures within 5% of the factory specification. An injector that's clogged will deliver less, and the spray pattern will be distorted, coming out in a stream rather than a fine mist. An injector that's leaking will deliver more than it should, and fuel will continue to dribble even after the pulse signal stops. Once the faulty injectors are identified, the Japanese method is to treat them in place using a series of progressively stronger solvents introduced through the fuel rail. The first solvent is mild, designed to soften surface deposits without attacking seals or plastics. The injector is pulsed repeatedly while submerged in this solvent, which in a shop setting is done by capping the rail and filling it completely. After 10 minutes, the injector is retested. If flow improves, the treatment continues. If there's no change, a stronger solvent is used. This process repeats up to 3 times, with each solvent being more aggressive than the last. What makes this method so precise is that it's data-driven. There's no guessing. You know the exact flow rate before treatment, you know the target flow rate, and you know whether the treatment is working in real time. If an injector responds to the first solvent, you know the deposits were superficial. If it takes the third solvent to show improvement, you know the contamination was severe. And if no amount of solvent restores the flow, you know the injector is mechanically damaged and replacement is the only option. This eliminates the common problem of replacing injectors that didn't actually need replacing, or worse, not replacing injectors that are truly beyond repair. The cost of this service varies widely depending on location, but in Japan, it's typically around $200 to $300 for a 4-cylinder engine. That includes testing, cleaning, retesting, and a written report showing the before and after flow rates. Compare that to $600 for a set of new injectors plus labor to install them, and the value becomes obvious. The only downside is availability. Not every shop has a flow bench, and not every technician knows how to use it properly. But if you can find a shop that offers this service, it's worth every cent. Number 2. Combustion chamber deposit removal via intake treatment. Here's something that might surprise you. Sometimes the problem isn't the injector itself, but the environment it's spraying into. If the combustion chamber is covered in carbon deposits, if the intake valves are caked with oil residue, if the piston tops look like they've been dipped in tar, the fuel can't burn properly no matter how perfectly the injector is spraying it. The Japanese recognize this and treat the entire intake and combustion system as one interconnected unit. Their method involves introducing a specialized foaming cleaner through the intake manifold while the engine is running at elevated RPM. The cleaner is delivered through a hose connected to a vacuum port on the intake manifold, usually the brake booster line or PCV inlet, As the engine draws in air, it also pulls in the foaming agent, which expands as it enters the lower pressure environment of the intake. This foam coats everything it touches: the back of the intake valves, the intake ports, the throttle body, and eventually the combustion chamber itself. The engine is kept running at around 2000 RPM for 5 to 10 minutes while the foam does its work, breaking down carbon, dissolving varnish, and lifting off baked-on oil residue. What happens next is dramatic. After the foam treatment, the engine is allowed to idle for 30 seconds, then it's shut off and left to sit for 10 minutes. During this time, the chemicals continue to penetrate and soften the deposits. When the engine is restarted, thick white or gray smoke pours from the exhaust as combustion clean. The Japanese perform this treatment every 40,000 to 60,000 kilometers as standard maintenance, not as a fix for a problem, but as a way to prevent problems from developing in the first place. The cost is minimal, usually around $80 to $120, and it can be done in under an hour. One word of caution that Japanese mechanics are very strict about: this method must never be used on engines with severe oil consumption issues. If the engine is burning oil, adding a chemical foam to the intake will only make the smoke show worse and can potentially damage the catalytic converter with excessive hydrocarbons. Always fix oil consumption first, then clean the combustion chamber. Order matters. We're almost at number 1, but before we get there, I want to hear from you. What's the highest mileage you've ever seen on a car with original injectors? Comment below, because what's coming next is the single most important principle that makes those high-mileage engines possible. Number 1. The supreme Japanese philosophy of continuous prevention. We've reached the top, and here's the truth that every master mechanic in Japan will tell you. The best way to clean fuel injectors without removing them is to never let them get dirty enough to need aggressive cleaning in the first place. This isn't a technique. This isn't a product. This is a mindset. It's the understanding that maintenance is not something you do when something breaks. It's something you do to prevent things from breaking. And when it comes to fuel injectors, the difference between a preventive approach and a reactive approach is literally tens of thousands of kilometers of trouble-free driving versus constant issues, poor performance, and expensive repairs. The Japanese maintenance philosophy is built on intervals, not symptoms. They don't wait for rough idle. They don't wait for check engine lights. They don't wait for poor fuel economy. They clean injectors every 30,000 kilometers whether they seem to need it or not. They use top-tier fuel every single fill-up whether it's convenient or not. They perform high-temperature driving cycles every month, whether they feel like it or not. The discipline is absolute, and the results speak for themselves. Japanese cars routinely surpass 300,000, 400,000, even 500,000 kilometers on original fuel injectors, original oxygen sensors, original catalytic converters, all because those components were maintained before they had a chance to fail. Let me break down what a true Japanese preventive schedule looks like. Every 5,000 kilometers, a bottle of high-quality PEA-based additive goes into the tank on a low fuel light. The car is then driven gently for the first 50 kilometers to allow the chemical to soak into deposits, followed by normal driving until the tank is empty. Every 30,000 kilometers, a professional cleaning service is performed. This could be pressure-regulated cleaning, ultrasonic treatment, or intake foam cleaning depending on the engine type and driving conditions. The choice of method isn't random. It's based on diagnostic data from the previous service. Every 60,000 kilometers, a full system inspection is done, including flow bench testing if available, combustion chamber inspection via borescope, and fuel pressure testing to ensure the entire delivery system is operating within specifications. But here's where it gets interesting. The Japanese don't stop at the injectors. They maintain the entire fuel system as a unit. The fuel filters changed every 40,000 kilometers, not every 80,000 as some manufacturers suggest. The fuel pump strainer is inspected and cleaned every 100,000 kilometers. The fuel tank itself is drained and flushed every 150,000 kilometers to remove sediment that accumulates at the bottom. Why? Because a clean fuel system means clean clean injectors. If you're pumping contaminated fuel through pristine injectors, those injectors won't stay pristine for long. There's also a seasonal component that most people overlook. In Japan, before winter, before summer, before rainy season, the fuel system gets attention. Before winter, a fuel stabilizer with anti-gel properties is added to prevent wax formation in diesel engines or moisture accumulation in gasoline engines. Before summer, a high detergent fuel treatment is used to prepare for the increased evaporation and deposit formation that comes with high temperatures. Before rainy season, a moisture control additive is used to prevent phase separation in ethanol-blended fuels. It's systematic, it's predictable, and it works. Now, I know what some of you are thinking. This sounds expensive. This sounds time-consuming. But here's the reality check. The total cost of preventive injector maintenance over 300,000 kilometers is around $800 to $200, depending on your region and the methods you choose. The cost of replacing a full set of injectors once because they were neglected, $1,500 to $2,500 plus labor. And that's assuming the clogged injectors didn't cause secondary damage to the catalytic converter, oxygen sensors, or engine itself, which they often do. The math isn't even close. Prevention is always cheaper than repair. But beyond the money, there's something else. There's peace of mind, there's reliability, there's the confidence that when you turn the key, the engine will start smoothly, run quietly, and deliver the power you expect without hesitation, without drama, without surprise repair bills. That's what the Japanese method delivers. Not miracles, not shortcuts. Just consistent, methodical, intelligent care that respects the engineering that went into the vehicle. A master mechanic in Kyoto once told me something that changed how I think about car maintenance forever. He said, "An engine is not a disposable appliance. It's a machine built to outlast its owner if treated with respect. And treating it with respect doesn't mean spending a fortune. It means paying attention, following a schedule, and understanding that small efforts repeated consistently will always outperform large efforts done sporadically." So here's my challenge to you. Pick one method from this list, just one. It doesn't have to be the most expensive or the most advanced. It just has to be something you commit to doing regularly. Maybe it's switching to top-tier fuel. Maybe it's adding a quality additive every 10,000 kilometers. Maybe it's taking your car on a monthly highway run to burn off carbon. Whatever it is, start today. Not next week, not next month, today. And 6 months from now, come back to this video and tell me what changed. I guarantee you'll notice smoother running, better throttle response, improved fuel economy, or all of the above. If this video helped you understand something you didn't know before, if it saved you from an unnecessary repair, or if it just made you think differently about how you maintain your car, do me one last favor. Hit that subscribe button, leave a like, and share this with anyone who could benefit from it. The algorithm doesn't care about quality content. It cares about engagement.